Okay, let's take a look at some additional systems and determine for each of them whether they are linear and time invariant or if they just have one or neither of those properties. Let's start with this system. Y of t is going to be an integral function of x, and we're going to use the variable of integration tau here because we don't want to be using t for two different things. So we have a function of x integrating over its time variable tau, and y of t is going to be defined as the integral of that function from negative infinity up to time. So it turns out that this system, this integral system, is a linear time invariant system. So let's go ahead and prove that. From the last lecture, we know a system is linear if it has the additivity and the scalability property. Now we're going to focus on the additivity property. There are some weird examples of systems that would be additive but not scalable, but they are not the everyday sorts of functions that we run into. They have certain particular types of support on the time axis that we are not concerned about in this class. So we're going to focus on the additivity property. So to check for additivity, which is how we're going to check for the linear part of linearity, we say, well, if the signal x is made up of some number of components, and usually for our proofs we just say it's made up of two components, then a system has the additivity property if it doesn't matter what order I do the system application and the summing. So now in a real-world implementation, what we want to do is we want to have just one instance of the system, and we want the total signal to be the input, and then we get an output. And for analysis purposes, if the system is linear, and specifically if it is additive, for analysis purposes, we can say, well, let me make two conceptual copies of the system, and let me put the signals separately into each of them. And maybe this is, and it should be, an easier analysis problem, and I get out output 1, and I get here output 2, and then I add those together. If the system is obeying the additivity property, then y star is equal to y of t. And we have a way for analysis purposes to figure out what's happening, and we have a simpler way with less hardware to implement the real system. So let's see if this is true for the integral system. So we can calculate that the output y of t here is this integral that we have, and I can substitute in the definition of x of tau, or x of t, which is that it's made of the sum of these two parts. So let me substitute that in. So I have x1 plus x2 integrate over tau. Now you know from calculus that integrating the sum of two functions is the sum of integrating them individually. And it turns out that that property, you may remember from calculus, is because the integral operator itself is a linear operator. So since it has that property, this additivity applies to integration, and we can break it down this way. Now, if I look at these integrals, they just match what I have in the bottom diagram. This integral here says x1 alone is running through the system. And what does the system do? Here's the definition of the system. It takes the input function and it integrates it from its time variable. It goes from negative infinity to the current time. And that's exactly what this is. So this expression here is just y1 of t. And this other integral is just y2 of t. But since we also have this bottom diagram, we can see that the sum of y1 and y2 is also y star of t. So since y star of t is equal to y of t, since these two different ways of evaluating the system are equivalent, we can say therefore the system is additive and we'll say probably linear. But for our purposes in 3032, it is linear. The only way it wouldn't be linear is if it did not obey scaling. And for the normal types of systems we're looking at, for normal types of functions and normal types of integrals, you would not have a case where it's additive but does not obey scaling. So this is linear. Now, we also want to prove that it is time invariant. Let's do that on the next slide. So I will rewrite the system integral here. And for time invariance, we would say that delaying the input and then applying the system is the same, gives you the same result as doing it in the opposite order, applying the system to the input and then delaying the output. So that is a property, that is the defining property of time invariant systems. So we have an input signal x, we can apply a delay, and then we can apply a system to get an output. Then for our other path, we will take the same signal, but we will apply the system to it. We're going to call that top one y star. We'll call this one y. And then we delay. So we have a delay, and here we have the same delay. And then we get to, we know when we delay it, we replace t with t minus the delay. So if the system is time invariant, this path, which we call the result y star, taking an input, delaying it, and then applying the system will give me the same result as if I took the input, applied the system, and then delayed it. So the question is, are these two items equal? And they will be for the integration. Let's prove that a little more carefully. So we have y star for this function is just the integral of what was coming into it. So it is the integral of x of, now I'm going to replace the time variable t with a variable of integration tau here, and the limits are negative infinity to t. So I'm following a couple definitions. I'm following y star is the system applied to this signal. The system is defined right here. It says you take whatever the input is. In this case, the input is x of tau minus delay capital T, and you integrate it from the beginning of time up until the time at which the function is being evaluated. And the bottom path just tells us to take the system applied to the signal, so that's this y of t I have right here, and then delay whatever that output y of t is by capital T. So I take this equation and I delay this here by capital T. So now we're going through the bottom path. I want to take that equation, but I'm going to replace all the small t's with t minus capital T. So I get this integral, and that's my delay. And I can see that these two expressions are equivalent if I do a change of variables. So let's call the substituted variable u and set equal to the variable of integration tau plus the constant t. Then I have du equals d tau, and I can substitute into this expression. So now I have, let me solve this here to find out what my taus become. So my taus are going to be u minus capital T because of the substitution that I did. So now I need to replace all the taus with u minus capital T. So in the integral, I have x not of tau, but of u minus capital T. Instead of d tau, I have du. And now I have to adjust the limits to be in terms of u. So I take the old limit and I add capital T to it per the substitution. So negative infinity plus the finite value t is still going to be negative infinity. And then small t minus capital T plus capital T will just be small t. So small t and still negative infinity. And now we can see that this expression here matches this one here. The only difference is I have variable of integration called u, variable of integration called tau. That's arbitrary. They really are equal. Therefore, I can say that the integration is time invariant. Okay, let's look at this function. Let's have a system that takes y of t is equal to x at t divided by 2. So we have a time scaling system. And we want to know, is this linear? And is this time invariant? First of all, is it linear? With linearity, remember that I represent the signal as a sum of multiple pieces. Usually we use 2 unless we have a specific reason to break it down into more. And then I say, okay, let me look at the system the way we would implement it in the real world. The signal goes through and gets an output. And let me also, for analysis purposes, consider the effect of the system separately on the x1 and x2, getting these outputs y1 and y2, and then saying, does superposition apply? So if superposition applies, this output here will be the same as above. For now, I'll just call it y star because we don't know that it's definitely the same. But if superposition applies, if I have a linear system, then the function y is equal to the function y star. So on this diagram, we can fill in the values of the signals. So x is x1 of t plus x2 of t, and then the system rule that we're applying here, system t, says to get the output, you take the input and you replace the time variable with time variable divide by 2. So we are slowing down the function by a factor of 2. So over here we get y of t equals x of 1, t replaced with t over 2, and we get x of 2 with t over 2. And here in the bottom diagram, x of 1 through the system, we have y1 equals x of t over 2, and we have y2 equals x, that's x1 up above x2 of t over 2. We're just applying the system rules to those two parts, and we add them together. And they are equal using both methods. So this is a linear system. If I have two functions that I add together, and then I scale the time of the result, it's the same as I scale the time of the inputs and then add them together. Now let's ask, is this time invariant? So in time invariance, I do a different block diagram. I say, okay, start with the function x, and in one case I'm going to do a delay first, and in the other case I am going to apply the system first, and then here I apply the system second, and here I apply the delay second. And I get these two functions, and I see whether they are equal. So x of t delayed will be x of t minus the delay. X of t through the system, following the definition, is going to be x of t divided by 2. And then I apply a delay to that. The rule for delay is you replace all the t's with t minus the amount of the delay. And then here I apply on the top branch, I apply the system. So I replace all the time variables with time variable over 2. That's what the time scaling system says to do. So I have x of t is replaced with t over 2, and then minus t0. So now I can see that this time scaling system is not time invariant. These two expressions are different because it matters whether I do the division by 2 on time before or after I do the time shift. So let's do a quick sketch of a signal with this. Let's say I have this triangular pulse that it ramps up at a slope of 1 in 1 second and ramps down. And let's say that I do a time scaling factor of 2 and a time shift of 2 seconds. So if I do time scaling, then I have speeded up. So I have in 1 second, I do that. And then I'm going to do a delay of 2 seconds. So I take that and it starts at 2 seconds instead of at 1 second. Now here I do things in the opposite order. I do the delay first. So I delay, and my original signal now is going to, instead of starting and at 0 and ending at 2, I add 2 to that, so it'll start at 2 and end at 4. And then I apply the system. So then I apply the system, I apply time scaling, so I speed up the system, so what happened at time 2 is now happening at time 1. And what happened at time 4 is happening at time 2, and the peak at 3 is happening at 1.5. So the delay of 4 itself got, the delay of 2 itself got scaled down to a delay of 1 in the second case, but not in the first case. So those are not equal, therefore the system is not time invariant.